Thank you very much for the invitation. I think it's a really great workshop. And I hope this is an entertaining talk to us as being the last talk. So what I want to show is how we can integrate machine learning in a closed loop of control systems. And just to give you a little bit of background, so I started with control theory, and I think somehow this is still kind of my home field. And then during my PhD, I applied controls to robotics to enable robots to do tasks on their own. And there we encountered the limitations of classical control theory, and I started working on machine learning techniques for robotics. And so this talk is focused on robotics, but if you are not working with robots, you can kind of replace robot with any dynamic system. None of our methods are particularly focused on robot properties. They would work for any dynamic system. So the work is really at the interface of those three fields: control theory, robotics, and machine learning. And everything you see is due to a great team of students. But it's not only the students whom you could meet if you decide and want to come visit Toronto, but also we have a number of different robot platforms with which we work on a daily basis. And just to give you a sense of how that looks like, I have kind of a summary video. So this is our lab. Here we fly 25 small quadrotor vehicles in a coordinated way. We have some applications of multi-vehicles for monitoring tasks. We also fly outdoors at speeds up to 55 kilometers per hour. And we experience winds up to 24 kilometers per hour. And here, this is a collaboration with one of my colleagues in Toronto, Tim Barfoot, where we fly based on vision only and no GPS. We also have off-road vehicles, which we use for experiments, and we have been participating in a self-driving car competition sponsored by General Motors, which we won in the past 2 years. And more recently, I'm interested also in mobile platforms that incorporate a robot arm. And so all of that is towards a vision where we see robots navigating our skies and roads, collaborate with us in the home, and even in the workplace. And if we look at these next generation robotics applications, what they have all in common is that we have large prior uncertainties. It's really hard to, at the beginning, describe all the situations this robot will encounter. Still, they have to actively make decisions, and we expect them to be safe and high performance. A typical approach that we know from controls is that you start with a system model. You identify this model using data, and then you use that model to design a controller. And this has worked really well in controlled environments. And those tools have also allowed us to study the robustness towards model error. So we can quantify when does our approach work, even if our model is not perfectly correct. And it allows us to explicitly take into account safety constraints, in particular if we look at formulations like model predictive control. So if you look at the applications in robotics, what control has to offer is it's using models, designing feedback controllers that allow these, the robots to do their tasks. We can guarantee safety, and we can design controllers for the worst case, which is robust control. So the worst case model errors, we still want to design a controller that is safe in that case. However, if we look at these type of applications, the worst case may not be, optimizing for the worst case may not be what we want, because for example, for self-driving car, all the different weather conditions it could encounter, if we design a controller that can handle all of them, maybe it's too conservative on a standard day. Or if you think about all the different kind of human sizes and weights such an exoskeleton has to work with, if you kind of make it work for the worst case or for all kind of possibilities it can encounter, it may be not good enough for the particular case it is applied to. And so that motivates systems that on their own, online, as they operate, learn and adapt. And that is something that's typically not part of standard control systems. Of course, there are approaches like adaptive control, but adaptive control is a model-free technique that just quickly adapts to the changing environment and doesn't keep that knowledge around for the future. On the other hand, we have classical machine learning. So to summarize, the performance here is limited by our system understanding. So we assume we may not have a good description of the model. We have model uncertainties, and the best thing we can do is work with the worst case. On the other hand, there's traditional reinforcement learning from the computer science community. And the standard approach is to not model the system, directly go from use data samples to optimize a controller policy, right? And so a typical setup looks like this. The learner, you can also replace learner by controller, tries different actions. This affects the robot and the environment, and we see what effect this action has in terms of which state the robot is in after that action has been applied, and also what reward it got, and the reward kind of represents how well we did in terms of the task we want to achieve. And so the setup is very flexible. It collects relevant data for the task because we collect kind of the reward values. Typically, it optimizes performance in terms of expectation. So I want the average performance to be good. And it has been, extremely successful in environments such as, games, simulation environments, and lab settings, such as this one, which are, all of them are quite controlled environments still, right? There's very little uncertainty in any of them. It's just that we optimize a policy for a complex system that we may not know how to design a policy otherwise. So if we compare it to control, it's kind of a lot of complementary properties. Machine learning has been great in collecting data, learning from that data, also studying this trade-off between exploration and exploitation. Exploring meaning, is it better to collect more data, or do I make decisions based on the data that I have right now? So this and work towards my task and task completion. So this trade-off of exploration and exploitation, and they look at the average case. But usually what those, at least vanilla techniques, are not really good at is safety and data efficiency, because they start from just data. A lot of data is required, and typically safety constraints in the worst case are not explicitly considered. And so here the safety is limited by the lack of the system understanding. So they make no assumptions about what the system is like, but then they also have a hard time guaranteeing safety, right? And so a lot of the work in my group has worked on combining models and data with the goal of applying it in robotics, where we want to learn and adapt online and still guarantee safety. So let's go back to the kind of traditional controls. So if we have robots models, even in control, those models are always just a partial summary of the robot's behavior. But no model, every model is an abstraction of the real world. And so I look at the typical control setup, where we have an input U and an output that we can measure Y. And then one way to describe the behavior of the robot is by this kind of difference equation, where we have a model that maybe get us quite far, an a priori model. So that's something that we know about the robot ahead of time. And especially in robotics, we have a pretty good understanding how these systems behave in general. But then there may be unknown components, and I split them up into a component that may be systematic and noise, like process noise. Just something, whenever I apply an input, I may not perfectly get the same output. And the reason can be that the process itself is noisy, or that my measurements are noisy. But both can be the case, right? And noisy process could come from some environmental factors like wind or friction. That's not always the same. And so for this kind of setup, control has standard model-based feedback control has still been very successful, despite the fact that our model is always, an approximation of the real behavior of the robot. And so typically a feedback controller would take the system state, some reference signal, and then compute the input. And this kind of baseline controller is based on a model, or is often based on a model. And we can do amazing things with this. I mean, this is completely model-based, even so these systems are complicated. This is a distributed model predictive approach for planning the motions, and the robots only see their neighbors. They only know the knowledge about their neighbors, but still they can coordinate, fly through that hula hoop, and transition to the next side. Even so, our model didn't take into account all the different aerodynamic effects that are happening. Right? But still, the controllers can do really well. Same here, quite challenging task. We recently started working on is catching ball with mobile manipulators. Again, this is purely model-based, right? But then there are tasks where we get to the limit of what a model-based controller can do. And for example, one I experienced this the first time is if we wanted to raise a slalom with one of these quadrotor vehicles. And so when we do this, and we do a typical setup where the reference that we send in is our actual desired task, so our desired trajectory. And so the desired trajectory here is the blue line. And I send this as the reference. Then what I see at the output, these are the multiple colored lines, is that I have pretty large repetitive errors. And so you would think you can do somehow better, right? And so if you want to see this in experiment, this is kind of, it was supposed to work based on our model, right? And the same here, this is a ground robot, and should drive along this path, and then it gets off the path. So what I want to do in this talk is, based on this motivation that models can be useful but have their limits, to show you how from a single robot doing a single task, and we allow a potential training phase to collect data, and we have some unknown static conditions, which you saw in the example I just showed, so some systematic errors. I want to show you how we started and worked on the simple problem, and then eventually extended it to how can we learn multiple tasks with multiple, possibly different robots, continuously improve as the robot operates, and also deal with changing conditions. And so let's start with a single task learning, and we allow a training phase. So a very simple setup that we can do is, instead of sending the reference, the desired output as the reference, can we modify the reference in a way, iteratively, such that we get the desired output? And so the way how you can model it is we set up the system with an underlying baseline controller such that the mapping from a sequence of inputs R, this is the bold R, to the sequence of outputs, which is the bold Y, is systematic. So it's a mapping, you can think of a matrix that maps this large R vector to the Y vector, the bold R vector to the bold Y vector, right? Now, how can we improve this? We start with an initial reference trajectory that we send for the full task that is our desired output, but then we start modifying it based on what we observe. So based on what we observe at the output after executing a full task, we update our reference. And so we do that by saying the new reference is our old reference times, and this part is it takes into account the error that we see in the output. So how much are we away from the desired output? And then m hat is a representation that tells us, that maps output errors to changes in the reference. So how much do we have to change the reference to compensate for this output error? And then based on the setup, because we put it outside of the feedback loop, we have input-output stability still, and we can also show that the tracking error converges. But the interesting part is that what we use here for this m hat is our simple model that we have of the system, that we also used for the controller design. So this simple model is still good enough to tell us how I have to change the reference to make a small change in the output. So it tells us the direction of correction. So if I am a little bit too far left, what does that mean in terms of in which direction do I have to move my R? So we don't learn the gradient, basically. We use that from our approximate model. And then this architecture helps us in terms of just making this safe. You know, we work with flying vehicles. We don't want to crash them all the time. And so the result looks like this. So we start learning, and we start above the poles. And it converges quickly. So after 3 iterations, you know, we gradually adapted the reference, and we can do this task. And then we can change the configuration of the poles and do other slalom configurations, but every time we have to relearn from scratch. So the result that you saw at the end, there was still a learning process, and that was the result of it. So we can learn any configuration, but for each configuration we need a training phase because the correction is very dependent on the task I want to do. Right? And here you see another example. The vehicle should do a triple flip. Maybe I should stop briefly. So triple flip means it starts in hover, so no motion. Then it should go up and do 3 times 360 degrees of rotation, and then come back to where it started and stop there, right? And so if we look at this, if we just use the model that we had, there are so many complicated aerodynamic effects that are even hard to describe qualitatively. But so this is after the 7th iteration, it's still pretty bad. And then it gets better over time just by adjusting this input trajectory, and eventually lands there. And you can do this up to 70 iterations, and it kind of just does the same task. It converges, and you see if you run this for a long time, it eventually even adapts to the fact that the battery gets trained and adapts to the weaker battery, basically. And you can learn pretty challenging tasks that we wouldn't do how to program otherwise. But each task we learn from scratch. So the first step was how can we learn multiple tasks, right? And so the tool for that is, let's learn a model instead of just a correction of the input. Yeah. So.
Maybe you're about to say this actually. Can you use the reference trajectory as a supervision signal for retraining the model? Is that like?
It goes in this direction. Yeah, yeah.
Okay.
It goes in this direction. Are there other questions? Yeah.
So how good has the model to be such that this works? Like the initial model guess, how good or how, and also how to choose the update rate of the reference trajectory?
Yeah. So the question was how good does the initial model have to be for it to work? We don't have no real formal analysis for nonlinear systems, which this is, but intuitively it needs to be correct to first order such that the derivative is correct. So you could say that, yeah. Do you want to add something?
We can discuss in the break, but there is some theory that you can make for nonlinear systems.
Yeah. So we haven't analyzed this in too much detail. The update rate for the input, that input trajectory is not that important. Ultimately, it limits the kind of motions that you can do, right? But if you do lower update rates, then this just means that you have to work with that, and maybe that restricts the type of motions you can do. So if we go to multitask, yes, what about learning a model? And so the setup that we do is we learn the inverse of this closed loop system. And we know from control theory that like a standard closed loop system would never perfectly track every reference trajectory. I can design a controller that perfectly tracks one trajectory, but all of a large range of trajectories is difficult. But we can put this model inverse, closed loop model inverse, and then the idea is that the mapping from from the reference input to the output, so from y desired to y, is a unity map. So it's perfect tracking. This is not new, right? If you have a perfect model, you can do this based on the model, but it ultimately relies on cancellations. So that makes it tricky in practice. And so we learn that instead of taking this from the model, we learn it. And if we still make some assumption what this gray box is, even so we assume now we don't know anything about this black box, right? We don't know anything. But we say, if we say, but it may have this form, this dynamic form, then from control theory, we can actually show that for perfect tracking, the reference here needs to be a function of y desired at time t plus r and at current state. And so that we can basically derive from control theory. So in a standard nominal case, it would be a function of the current state and the desired state r steps in the future, and r is basically the inherent delay of this of the gray box. And so that helped us a lot to design what the inputs features to this learning box should be. And we use the deep neural network, but you can probably use another nonlinear regression technique. But instead of somehow thinking that you need the whole history of the y desired as an input to this green block, you really need only the one value that's r steps in the future. And what r is, you can very quickly identify through a step response. And the guarantees are similar to before because we have this underlying stable system. As long as r is bounded, we can prove that the overall system is stable. And so here we collect now, we still have a prior training phase. We collect many pairs of r and y, right? And then we learn this inverse model. and then we can track arbitrary trajectories. And how we tested this is we allowed people to draw quite kind of complicated trajectories on a tablet, and then we fly them. And on average, we do an improvement of 62% on those trajectories, and we have been working on improving this further. The training data for identifying this was periodic motions only at different frequencies. And so here is a video how this looks like, and if you come to the lab, you can actually, and visit us, you can actually try this out. So you draw on the tablet, and then here you see the drawn line as dashed red line, and this is our standard controller that usually works pretty well. And now if we include the learning component, it gets significantly better. And so then people drew different trajectories. And now you see always the solution with a neural network included. You know, it gets better and does quite complicated motions. So this was one way to look at multitask by learning the model. There's more that we have been doing, but I want to focus the next step on, we always had this training phase, right? But if we operate robots in the real world 24/7, things may change and we want them to improve on the spot. And so in order to allow continuous improvement in a safe way, we looked at a probabilistic formulation. So instead of just learning one deterministic model, let's look at a probabilistic model error formulation. And so the setup for this is slightly different. So we now model the system and then use that uncertain stochastic disturbance model in a robust controller design. And so the setup is, as I showed you before, we have an a priori model, but we have an additional component that we want to learn. And we assume initially we don't know much about this model. And basically look at this. So if this is the input to G and this is the output, we know basically nothing, and we just assume there's a mean and a large bound for where this function lies with high probability. And to model this, we use a Gaussian process. And then we use robust controller techniques from control theory that guarantee that we find a stable controller for a class of models. And the class of models that we initially consider is, we know F, and G is just represented by this Gaussian process. We know basically almost nothing, just maybe a lower and upper bound on where the values may lie. And then we solve this problem of find an input sequence that minimizes the expected cost, subject to the fact that we have this stochastic robot model, and we want to have high probability constraint satisfaction. And so how this Gaussian process works is, as we operate, we get more data, and we get more information about the underlying function. And the Gaussian process, if we have a data point, it not only tells us something about that particular input, but also about the neighboring values. So we kind of decrease the uncertainty envelope in the neighborhood of that point. And the reason for that is that we assume for G, for the true G, we assume a maximum rate of change. And so the function cannot suddenly jump. So there's a smoothness assumption. And therefore, we can kind of interpolate and extrapolate from data points that we get. But then we use this kind of nonlinear function with its probabilistic bounds in a robust control framework. And this way we have shown, depending how you incorporate which robust controller framework you use, we can show that the tracking error can be made arbitrarily small and that we can have constraint satisfaction, for example, staying within state and input constraints. And I want to show you one example on an off-road vehicle. So here, the vehicle, we use model predictive control, and we use a standard model predictive controller. And if you don't account for any model uncertainties, you see that we have quite some deviations from this desired path. And of course, we set up the experiment such that it fails, so it violates some of the path constraints because our model is not correct, and we do model predictive control on with an incorrect model. The model is just a kinematic model of that robot. And then now we can start and learn this unmodeled dynamics. And what you will see in the experiment is that if we look at such a framework and we use a model predictive controller here, what happens is initially we have a large uncertainty in our system. So even if we know perfectly where the robot is, and then we do prediction, so we decide on a sequence of inputs over the next, let's say, 10 seconds, then we don't know for that sequence of inputs where we will end up, right? Because our model is uncertain. So it can be anywhere in this red shaded area. So what the algorithm automatically does is it slows down the motion of the robot over that same prediction horizon such that the uncertainty envelope stays within the path bounds. And why slowing down? Because typically we have a better idea how a robot moves at lower speeds, and at higher speeds those dynamics become more important. And so but eventually, if we gather data, and we do that in real time and update the model in real time, then our uncertainty shrinks and we can eventually drive faster without worrying about violating those path constraints. And so that's what we see in the experiments. And you see it's really working with the worst case, right? For example, these bounds, you can say these are the 3 sigma bounds of a Gaussian. So they are probabilistic guarantees, but worst case guarantees. And so here you see it for the simple experiments that I showed you before. So we drive initially quite slowly because we make very conservative assumptions about what these unknown functions could be. And then after driving it for the 3rd time, we have a pretty good sense of the unknown function. And you see a smaller uncertainty envelope and a faster motion. And then we did long-term tests of 1 kilometer around our building. And so here you see trial 1 and 3. On the left is the first time we drive it, and on the right it's the 3rd time we drive this off-road path. And so this actually allowed us to drive our robot faster than we had ever done before. And we were not comfortable to do beforehand. So you would need to really run to follow the robot. And so this section of the path was already finished when we did it the 3rd time, and in the first run, the robot is still going.
Is it a nonlinear MPC?
Yes, that's a good question. So because the Gaussian process is a nonlinear, it has to be nonlinear MPC. So yes, you have to solve a nonlinear optimization problem, right? So whenever, if you want to really do formal proofs, a lot has resulted to look at the linear case just because of the optimization problem. So a probabilistic formulation, I think, is really important if you want to do online improvement in the real world. where you start working from a worst case scenario, and then as you gather more data, you get more confident in your model. So you can also view the Gaussian process as modeling your uncertainty about the system behavior, right? And so the last step is, how can we go from a single robot to multi-robot? In multi-robot, I mean more like, if I have learned something with one robot, can I use it on another robot? And how can we deal with changing conditions? And this is, I mean, still ongoing work. I wouldn't say this is solved at all, as probably any of those things I've showed you. But one way we have started working with this is by doing very fast adaptation with kind of long-term learning. And if I look at the same setup, dynamic setup as before, now this unknown function may change over time, right? This could be weather or wind or anything that may change as we go. So it means that if I now apply the same input again to my system, the next state may be a different one than what I had experienced before. And so one way we have been dealing with this is have a really fast underlying adaptive control loop to compensate for these changes and make this dashed box still look like a repetitive system. System. So especially in the L1 adaptive controller or any reference model adaptive control, the adaptive controller tries to make this dashed box behave like a reference system or close to a reference system despite disturbances. And so the adaptive control now tries to guarantee this systematic linear input-output behavior, or systematic input-output behavior, and usually they try to, we use linear reference models, so it's a linear input-output behavior. And then you can still do various forms of inverse model learning on top. And the guarantees are similar to what we had before, since adaptive control, under some assumptions about what disturbances you experience, can give you guarantees. You can provide guarantees for this overall system. And so here's one result of how that can look like. So we learned slalom trajectory with this quadrotor. And we had as underlying controllers either a standard PD controller, PID controller, or this adaptive controller in green. And so over multiple trials, repetitively doing this slalom motion, we get better. And you see also how quickly we can get better with our techniques. And then at iteration 10, we just switch out the robot, and we use a slightly different one. And so if we have standard underlying controllers, then basically we need to relearn this task, right? But if we have this L1 controller as an underlying controller, we can reuse this higher level reference information. So we can we don't have to relearn in this case. So I do think that also shows you how hierarchy can be important in all these tasks, hierarchy of different methods. We also tried to transfer not only from one system to another, but also doing a different task at the same time. And you can imagine that this works equally well, because I showed you before that we can do model, on the high level we can do model learning and learn one model and then do any hand-drawn trajectory. And now we do the same, we just have this underlying adaptive controller. And so here's some results. So basically, we collect data from the source system, so this quadrotor, and then we use that data to do any of those 6 tasks. So we do one task with the source system, and then we test it on 6 other tasks of the target system, and then we do this for all combinations. And so here are the results. So what the this dot, the white filled dot is if we would do this task with our second quadrotor without any learning. So these are those dots. And then the solid red dots are if we learn that particular task with that particular robot in this kind of iterative learning fashion. And that's basically the best we can achieve, at least with the methods we know. And the box plots is if we transfer from any of the 6 trajectories to that one trajectory, and you see that we get really pretty good for any transfer configurations. So it works really well. So overall, we can get a 47% error reduction with this framework. So I showed you a bit of an overview of what we have been doing, more starting from a controls perspective in terms of incorporating data into the closed loop. I still think there are many open questions. Also, several of the tools we do have done, could have control theory people look at and provide even more stronger proofs. But how I see this in the big picture is what we'd like to do in robotics, and that's probably actually this graphic would apply to any feedback control system, I think, is on the one hand, we want to increase the complexity of the system and the operating conditions, right? Meaning larger networked systems. If you think about power systems, in robotics, this means more complicated robots operating in complicated environments such as our homes. So on the one hand, we aim for increasing the complexity of the system, but also the complexity of the task. Right? We want to, in standard industrial robots, we just have to do a single task very well, but eventually we want to give very high-level specifications, and they should be able to do these kind of complex missions without us telling us exactly how to do it, and eventually also interact with the environment and other agents. And so, yeah, industrial robots would sit here, maybe self-driving sits somewhere here on this kind of, on these 2 axes. And then this general household robot that we all aim for at some point, or would love to have, is, one of the most difficult ones. And so if we look at this, a lot of work that we have been doing, it just uses model-based planning and control, and we can already do a lot whenever we have sufficient prior information about the model. But if not, then we can learn a single task, or we can learn a model that allows us to do multiple tasks. We can even look at guaranteeing safety. But really, I do think if we want this seamless interaction of technical systems with the physical world, which is up here somewhere, it's really hard to do that with models. I mean, ultimately, you would eventually need to model humans, which is, I don't know, very difficult. So I think there's many open questions here. But from a robotics perspective or general control perspective, I think that's what motivates a lot of the research in learning. So what is next? I thought it's kind of in this workshop, it's nice to also kind of look at what could we do better. And so I think, there's a lot of lack in understanding how learning works for dynamic systems. And then you can test this on benchmarks or compare different techniques on benchmarks, and eventually and benchmarks represent kind of simplified scenarios that have properties that are close to the real application, and then eventually you want to test it on the real application, right? And so I think we are used to going back and forth between application and theory, right? Sometimes we see something in the application and then we go back and check it in a simplified problem, and then we develop the theory, or vice versa. The theory can help us for example, what not to do in practice, right? Because it just doesn't work. So I think in engineering, we always have this back and forth, and I think for learning, for dynamic systems, we should also approach it in this way. And I think one really interesting part that is also interesting for any machine learning people in this room is that robotics or generally dynamic systems have properties that have been often overlooked in machine learning. And in the machine learning benchmarks, which some of those I showed you at the beginning. And I just want to highlight what I think is really specific to robotics and dynamic systems in general, and should be dealt with when we deal with machine learning for those systems. And so one is the robot behaviors and general dynamic system behavior is always uncertain. I think there's always noise in the process, there's always noise in the measurements, and that needs to be studied, and we need to make sure that things work despite that noise, and we saw that in your talk that Q-learning had problems with this type of noise. So I think that's important, and something that many traditional reinforcement learning problems don't have. Then we have those constraints. If we have real systems in the real world, we have to make the dynamic system or the robot adhere to those physical constraints, and that has to be a central part in any general reinforcement learning approach. And here you just see the off-road path that we did with our vehicle from the top, and it had to drive through fence openings and close to trees, and we don't want a car-sized robot to drive off the path, right? Then robots can actively learn, and we can explore that. And I think Andreas Krause showed that video where we safely enable a robot to actively try out different controller parameters and learn that. So we can leverage the active part. So in many standard machine learning problems, you just get a data set and you learn from that. But here we can actively search for data that is useful for our learning task. And then ultimately, robots operate in changing environments. So I don't have which I highlighted a little bit at the very end of the talk. But we also operated our off-road robot over 5 months. And this was from snow cover to spring vegetation. And we want the robot work in all these conditions. And then ultimately, robots are complicated systems and make decisions at very different time scales. And I think that's a big open question, how to deal with this well. I mean, I showed you the quadrotors, but basically all the learning I showed you was on the position part, right? But there are many underlying controllers, the lowest level controllers sending inputs at 1,000 hertz. And so how do you deal with this? So overall, I think if we aim for performance and safety in robotics applications or any control application where we have prior uncertainty in the model, I think we can. The combination of machine learning and control is really powerful, and machine learning is the science of data and inference, and can help us to boost the performance of these systems. And control theory for me is the science of feedback. It's the field that has studied these closed loop systems for a long time, and I think can really help also to define important performance metrics for dynamic system learning, including stability, performance, robustness against model errors, and constraint satisfaction. Yeah, thanks.